So, looking at this week, we've got implicit differentiation. We're going to wrap that up today, talking about evaluating an equation at a particular point, evaluating the derivative at a point. And then also second derivative stuff, implicit differentiation. The rest of the week is going to be on this thing called related rates. So tomorrow is related rates intro, then related rates basic, then related rates advanced. And you might be like, whoa, I don't even know what related rates is. Well, you're going to like it. It's one of our first real dives into a very applicable situation dealing with calculus and visual. We've got pictures and diagrams and animations, and it's going to be a lot of fun. It's fun calculus, which is pretty fun. We also have a quiz, a memorization quiz, dealing with chapter 2, chapter 3 stuff, whatever that one handout is. We'll make sure we have it, as well as a new derivatives handout that I'm going to give you here before the end of class. So definitely want to get that in your hands so you can start looking over that before you go to sleep every night for memorization purposes. Okay. As always, all previous memorization quiz material is capable of being on this one. So, all right, let's go ahead and look at a problem. This looks maybe something like one of the problems on the back page. This is find the slope of the tangent line of this equation right here at the point 3, 1. All right, so if you put this down on your notes, we've got 3 times x squared plus y squared equals 100xy. This is sort of a crazy problem here. So what we're going to do is we're going to find the derivative. This kind of help remind us about how we did that implicit differentiation. So one of the properties of derivatives that we saw before was that if you have a constant times some expression, then the derivative of that is just going to be that constant times the derivative of that expression. So we're just going to pull this 3 down, and then we're going to put maybe a bracket since it's going to be multiplied by the derivative of all the rest of this stuff. Okay? So the derivative here, I'm looking at x squared plus y squared, and that whole entire quantity is squared. So we're going to treat this like a unit. So we'll bring the 2 down here, pop down the 2, keep the inside intact, x squared plus y squared. Power down that exponent to the first, but I'm not going to write the first. Then multiply that times the derivative of the inside. So since I'm multiplying this entire term times the derivative of the inside, then I'm going to put parentheses here. Class, what's the derivative of x squared? 2x. What's the derivative of y squared?
2y dx dy over dx.
2y dy over dx. Very good. That's the whole idea of the chain rule and applying that to our implicit differentiation. Okay, well that's actually not too bad. That's everything on the left-hand side. Over there on the right-hand side, we have 100 times x times y. What are you thinking when you see this right here? What sort of rules are you thinking?
The
Product rule. Good call, Nick. Let's maybe group that 100 and the x together as one term and then the y as another term. So product rule is the first times the derivative of the second plus the second times the derivative of the first. So let's go to it here. The first, so 100x times the derivative of the second. What's the derivative of y, class?
dy over dx.
dy over dx. Plus the second, so that's going to be y, times the derivative of the first, the derivative of 100x. 100. Okay. This one's kind of a messy problem, that's all right. We have 3 times all of this, and then there's a 2 times all of this. I'm not really pulling it out, but sort of rearranging this. The 3 times the 2, I'm going to write that as 6. And then, if you remember what our goal is our goal is to get all the dy over dx terms over here and all the non-dy dx terms over here. The issue is, though, we don't have a bunch of single terms like we've had up until now. We have this sort of craziness where this is inside, so we don't really have any alternative. We're going to have to FOIL. We're going to have to distribute that. So x squared and the 2x becomes 2x cubed. X squared and the 2y dy becomes literally 2x squared y dy over dx plus 2x times y squared plus 2y cubed dy over dx equals, and then I'll just probably copy this down again, 100x dy over dx plus, we'll write this as 100y. Okay, and then I have a 6 times this and this and this and this. Well, 6 times 2 is 12. 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 We'll just get rid of that 6 right there. How's that sound? That doesn't really help if you're tracing this back through, but for our purposes, it's fine. Alright, so I'm going to leave the dy over dx terms over here. So I've got this 12x squared y dy over dx, that takes care of this one, plus 12y cubed dy over dx, that takes care of this one. I'll subtract 100x dy dx from both sides, so minus 100x dy over dx, that takes care of that one. Over here on the right hand side, that 100y stays as is, and then I'll subtract this 12x cubed from both sides, so minus 12x cubed. And I'll subtract 12xy squared from both sides. It's possible that I'm making a typographical error or something like that. Anybody see any issues with the exponents or anything like that? Alright. If you do, just speak up here. You might catch it in a minute. I don't know if there are any. If you remember, the next stage in our process was to factor out a dy over dx. Okay, so I'm going to factor out a dy over dx out of each one of those terms. What's going to be left is a 12x squared y, a 12y cubed, and a minus 100x. And that is what I'm going to divide this side by and this side by. So the right-hand side has a numerator of 100y minus 12x cubed minus 12xy squared divided by 12x squared y plus 12y cubed minus 100x. What a problem, huh? But are we finished yet? What's the problem with this, Nick? We need to plug in 3, 1. That's right. So the notation for that would be dy over dx, and then with this evaluate bar, so vertical bar that goes all the way from the top to the bottom, evaluated at 3, 1. And it's literally just the substitution game. So 100 times 1 minus 12 times 3 cubed minus 12 times 3 times 1 squared all over 12 times 3 squared times 1 plus 12 times 1 cubed minus 100 times 3. And then you can just literally crunch the numbers. If you're okay, I'm okay. You'll come up with a physical number for that, and that would be the slope. Make sure you know how to type numbers into the calculator.
Okay, so for the numbers that are, when you're substituting, you know, the x and the y, would you put the exponent inside the parentheses, or wouldn't they be outside of the parentheses since you're substituting numbers for a variable?
You could do that. You could put them on the outside. That's not going to do any harm.
Okay.
In this case, they're positive, so it does absolutely no harm. If what you were saying is probably the more correct way of doing it, because if it was a negative number, you want to make sure that it was inside the parentheses. So I was doing that just for isolation purposes to kind of see that. But yeah, it'd be better to put it kind of like that.
Oh, okay.
If it's positive, it's not going to make any difference. But if it's negative, that's going to make when you type it into the calculator, that'll definitely make a difference. Okay, so look on the back of your paper, of your homework paper, and let's identify the problems that resemble this type. Chloe, do you see which problems look like this? 13, 14. Fortunately, 13 and 14 look a lot easier. So if you could do this monster problem, then you can do those problems. Agreed? Chloe, I'm talking to you.
Yes.
Okay.
Sorry, I'm trying to figure out the numbers.
You might wonder, ooh, Mr. Goddard, is there a way that, I know that this sort of like dy over dx evaluate that kind of reminds me of like the calculator, right? That's what Hector's thinking. He's like, is there a way we can type this on the calculator? All right, and the answer is no. Because your calculator doesn't have a y button. Actually, it does, but that's the alpha y, like the alpha numeric variable y, not the dependent variable y. That calculator has a function mode, and its function mode is always y equals, right? So we had a name for that type of a function from last week. You remember? Explicit, yeah. It can handle explicit functions. It can't handle implicit functions. Now, if your calculator had what's called a CAS, a computer algebra system, then it could. But these do not. So are there calculators that can handle this? Yes, there are. Is there an internet website that can process it? Sure. Wolfram Alpha is the best one for that, okay, in my opinion. But that would rob you of all this awesome algebra. I mean, right?
That's crazy that computer. I mean, the computers and the calculators can do all that.
Yeah. So, okay. Let's talk about the second derivative, and you might be like, this is going to be exactly like the first derivative. Well, let's find out. Let's go with that one that I had before. So here's the instructions. Find d squared y over dx squared. That's the second derivative. And here's our equation. X squared plus y squared equals 25. No big deal. Let's do it, class. Here, let's find the first derivative. What's the derivative of x squared? We'll have to do it. All right. What's the derivative of y squared? dy over dx, because y is a function of x. Y contains some sort of thing. Make sure I'm in the frame there, if you don't mind. What's the derivative of 25?
0.
0. We want the dy's on this side, so we have 2y times dy over dx equals negative 2x. And then we can divide both sides by 2y. We end up with dy over dx. I think we did this problem the other day, didn't we?
No.
Negative x over y.
I think, yeah. I think they might be in my notes.
I'll rewrite it up here. So dy over dx equals, I'm going to stash that negative up front. Up there. Negative x over y. That's the first derivative. So now let's find the second derivative. So d squared y over dx squared equals, if we're going to take the second derivative, what are you thinking?
Zeros.
Nope. Next up, Jeremy?
Oh.
She says quotient rule, beat you to it, that's right. So yeah, quotient rule. So low d high minus high d low over low squared we go. So here we go, so low, which is y, d high, anybody, what's the derivative of negative x?
Oh, yeah.
minus high, so negative x, d low, what's the derivative of y of y?
dy over d.
dy over dx. So I'm gonna put it, kind of like that, over low squared we go. So let me just back up a second, just kind of remind you what's going on. We're finding the second derivative. The way you find the second derivative is you find the first derivative, and then you take the derivative of it. So we found the first derivative implicitly. Now we're taking the derivative of that, and that function required us to use the quotient rule. So okay, so that's negative y, negative and a negative turns out to be a positive x dy over dx all over y squared. Well, that looks kind of weird. I've got an answer that has a dy over dx in it. I wonder if that's good enough.
Oh, no.
It's not good enough. Alright. Do we know what dy over dx is?
Yes. Negative x over d. Over
Yeah.
y now.
It's negative x over y. So, what we can do, this second derivative is going to require a substitution step where we substitute in that first derivative value up here. So we have negative y plus x, and then negative x over y divided by y squared. So it's sort of like we're doing the second part of the problem, but part of the second part of the problem requires us to know the first part of the problem to substitute it in. So that's going to be negative y minus x squared over y divided by y squared. And I just can't stand to see fractions of fractions there. So what we'll do is we'll multiply this one by y over y. So we've got negative y times y over y minus x squared over y divided by y. So we have negative y squared minus x squared all divided by y, all divided by y. Let's see if I'm making any sense. Sorry. This y in the denominator is squared. Let me slow down a second here. So what I'm doing is I'm taking that first term and multiplying it by y over y so that I have a common denominator in the numerator. So negative y times y is y squared minus the x squared, and that's all over the common denominator of y
squared.
And then all of that is over the is over the big denominator of y squared. So here, this making sense here? So then I'm going to do some fraction math. Instead of saying my numerator divided by the denominator, I'm going to say the numerator multiplied by the reciprocal of the denominator. So 1 over y squared. Am I losing you here, Chloe? Here's the numerator. Here's the denominator. Remember, fraction math is if you have something divided by something else, you can just say that numerator times the reciprocal of the denominator. So the denominator is y squared, so it's 1 over y squared. So we now have negative y squared minus x squared all over y cubed. So that's pretty good, okay? I will tell you though, and you can thank me that I don't make you do this kind of nonsense, okay? But like, when I was growing up and I was in your situation, all of our problems were always from the book, okay? And some of the answers were odd, and so we're like, yes, we can check our work in the back. And or some of our questions were odd numbered questions, so you could look at the back, and then we'd look in the back, and it certainly wouldn't have this. And you might say, well, maybe they would get to the common denominator, and you'd be like, okay, so they probably have something maybe like this. And the answer is no, they wouldn't have that. It They wouldn't even have that. They would have this. Negative 25 over y cubed. You're like, how do you turn negative y squared minus x squared into negative 25? Answer, you factor out a negative 1 and realize that you have y squared plus x squared. And look at the original problem. What's x squared plus y squared? 25. So this is what we would see as the final answer.
Oh.
You see what I'm saying?
Yeah.
So they would go back and that's great because I'd rather have a 25 than an x squared plus a y squared, you know, if you're doing calculations and stuff like that. Yeah, so simplifying it all the way down. And sometimes they'd even do even more weird stuff than that. And it would make sense, but as a beginning calculus student, I'm like, I just want to know if I did the derivative right. You know what I mean? Or did I get the second derivative right? Was I on track here? But you would have to, hopefully you got that right. And then you would do all of the algebra correct, just to be able to hopefully see. You might, you know,
So you have to
you
do
wouldn't
the
know
whole
if it-
thing right in order just to see if you did it right.
right, you wouldn't know if you had the algebra right, or the algebra wrong, or the calculus wrong, okay? I'm probably a bad teacher and expecting you to handle some of the algebra, but in all honesty, the algebra is always the hardest part of calculus. So, the calculus part is easy. I could teach my third grade son how to do calculus, right? I could say, hey, look, you take this number and you put it here and then you decrease it by 1. There you know, you just touched the power rule. You know what I mean? Okay? That's not really learning calculus, that's learning the mechanics of calculus, okay? But why is that? And what does this mean? And how do you apply it? And how do you do the chain? You know what I mean? That's what separates you from somebody who can just move pieces around. Okay? So there you go. I think if you look on the back of your homework, you will find some questions that look like that, yes? So 15 and 16 say, use implicit differentiation to find the second derivative in terms of x's and y's. And then 17 and 18 say, for each problem, use implicit differentiation to find the second derivative at the given point. I'm not going to do a problem like that, but you can probably imagine it's going to be sort of like a mix between this problem and the previous one, right? Only thing is once you get down to this stage right here, then you'll have an x and a y to be able to plug the values into, and you'll end up with something. So 15 and 16, the type of answer that I'm looking for is going to be an expression. 15 and 16, I'm looking for something in terms of x's and y's. 17 and 18, what am I looking for?
Slope.
Yeah, a slope. Well, it's the second derivative. The second derivative is not a slope.
Oh.
It's going to be a number, a specific number, like 1/5 or 22 or something like that. Okay? Neither of those are the right answers, by the way. Okay. Possibly we can look at that together. I do want to hand out this paper though. This is the derivative sheet which I was referring to earlier, which will be on your your memorization quiz. Would you like for us to do some of these together?
Yes, that'd be lovely.
The logarithm one maybe.
Okay, well, you'll learn that one like in 2 weeks when we talk about logarithms.
Oh, we're not doing all of them?
So, that's multiple questions at the same time. When is this test? Thursday. We're not doing all of them? That is correct.
Okay. Yeah.
So there's nothing on Friday.
We don't have school.
There's all kinds of stuff going on Friday, just
There's no school
not
Friday?
related to you and calculus.
Oh my gosh, this is such a good week. Really? I think I'm gonna go too. I think I'm gonna go Saturday. Kids this week now. Sign up. I'll get you the papers.
I have the papers.
You
I
do?
just need to sign it.
Sign them up. I'm gonna.
Alright, a couple things here. You might want to put at the top of your paper, C is a constant. U is a function of X. So you can think of U as some sort of mystery thing, you know, like as like what we've been considering Y, right? V is a function of X. Number one is asking about the constant multiple rule. What's the derivative of a constant times a function? And the answer is a constant times the derivative of that function. So you could write the derivative of the function as du over dx, but the way that we are going to write it is u prime. Just as one of the other alternate notations, dy over dx, y prime, f prime of x, all those different ways of doing that. So
Co-prime.
what's that?
Is that how would you pronounce that? Just
You wouldn't blend them together. You would just say c u prime.
Because U is.
I mean, like c u prime. All right. Go ahead, Ivan.
I was just gonna say it's because U is a function of F.
Yes. It's sort of like saying what is 3 times the sine of x? What would be so 3 is a constant, and then sine is a function of x. So what's the derivative of that? Well, it's 3 times cosine x. That's an example of what this one would be like. Okay. I can't do plus or minus symbols on this particular program, so you should put a plus or a minus right there. This is the sum and difference property of derivatives. So the sum and difference rule. That is, if you have two functions adding or subtracting, from each other, what's the derivative of those? And the answer is
derivative plus or minus the derivative.
Yeah, the other one. So it's going to be u prime plus or minus, whatever the case may be, v prime. An example of this might be x squared minus x cubed. If you want to take the derivative of that, it's going to be the derivative of this term minus the derivative of this term. Let's give a name to number 3. What's number 3 all about?
Rule.
Say it again? Product rule. I've heard y'all say it. So, if you want to put a little name here, so this is the constant multiple rule. This is the sum and difference rule. You don't have to name them. Sometimes it's helpful to help you remember them. This, of course, yes, is the product rule. So the first times the derivative of the second plus the second times the derivative of the first. Anybody want to? So Ivan and Stephanie, you can kind of participate pretty well. So give somebody else a chance. Nick, you want to give it a shot? You want to try to help write the product rule here for this one for u times v? Not plus, but u times. The derivative of the second, which would be so v prime. Keep going, Nick. There you go. If we had to give a name to number 4, what would that name be? The quotient rule. Y'all learned quite a lot of stuff here, huh? Okay, so Emily, what do you think?
So it'd be v times u prime minus u times v prime over v squared.
Look at us, abstract and algebraic. stayed up late last night. I need to work this morning. Alright, what's the derivative of a constant, class? 0. That's the derivative of a constant. The derivative of 7 is 0. The derivative of 42 is 0. The derivative of any constant, negative 99 is 0. The derivative of u to the n is
U.
no, u, no.
N. U.
U
Negative 1.
to the
N minus 1.
minus 1.
Yeah, sorry.
But wait, there's more.
dy.
Not dy over dx because we don't have y, but it would be
Oh.
du over dx, but we've been indicating that as
U
u
prime.
prime. Because remember, u is a function.
Oh, that's true. U kind of is like the dy.
I mean, you are. Yeah, so what you have to imagine that this is sort of like, what if you had x squared plus 3x to the 5th to the 10th, where so u is that whole function, so it's going to be 10 times x squared plus 3x to the 5th to the 9th times the derivative of the inside. That's why we have that u prime. Okay, so this is the power rule. Technically, it's a power rule with a chain rule kind of put together. All right, what is the derivative of x? 1. What's the derivative of the absolute value of u? We don't know yet.
Oh, since it's one.
So we're gonna leave that one blank. We might know some more. I don't know. Let's look down here. We don't know natural log. We don't know e to the u. We don't know logarithm. We don't know a to the u. You might be like, oh, we know a to the u. No, you don't. You know u to the x. All right. This is. There's a difference because we have u down here and then a number up here. This is a number right here with the function.
Oh, like to take into the power of that.
Yeah, this is like 2 to the x. We know x to the 2.
Mm-hmm.
We don't know 2 to the x. Totally different thing. But we do know these. What's the derivative of sine u? Cosine u times
U prime.
u prime, chain rule. Don't forget u prime on all of these. Derivative of cosine? Negative sine u times u prime. Tangent u.
It's tangent.
That's why we're having to do it, because so that you are just super fast on the draw here.
Secant squared.
Secant squared u times
U times derivative.
root u prime. Cotangent. It's co, so you know it's negative.
Negative cosecant squared.
U times
Prime. Yep. So yeah, the whole idea here of this memorization is so that we can do our problems quickly, and we're not waiting around. Dig them up in our notes.
Yeah, that's ridiculous.
So secant, derivative of secant is secant u tangent u times cosecant. I know it's negative. You know it's going to resemble that one. Cosecant u, cotangent u, u prime. And then the last 6 are the inverse functions, which we do not know yet. Hopefully we'll get to those. Those are more for believe it or not, Calc 2 type of a thing.
Wow.
But we might get to a little bit of them. We'll see.
It's pretty cool. That's
Okay.
busy.
So we know quite a lot. In fact, I think that you can find that page or a similar page in your calculus book, the front or the back. Who needs it? You've got that. Yeah, general derivatives. My paper's better.
What is this picture?
When is what? The implicit differentiation?
Yes.
According to this, tomorrow. 3M, 3N. That's gonna be busy night for you. Notes 311. I'll tell you what, I'll be generous here. I'll do notes 311 on Wednesday. That way, kind of spread the homework burden out. You'll still be learning about related rates on that day. So, okay. Today we talked about implicit derivatives at a point and second derivatives using implicit differentiation.